Last winter, Buffalo saw nearly 4 feet of snow fall in just 2 days. It was enough to bury entire neighborhoods and claim dozens of lives. But here is the paradox. As North America gets warmer, snowstorms are turning deadlier, driven by hidden forces far above our heads. What exactly changed in the atmosphere to make winters worse, not milder? And what happens if this keeps accelerating? Air that's just a few degrees warmer can hold a surprising amount of extra moisture, about 7% more water vapor for every degree Celsius it rises. This simple physical law, known as the Clausius-Clapeyron relation, means that as North America's winters get milder on average, the atmosphere is quietly loading up with more fuel for snowstorms. When a cold front sweeps down, all that added vapor can suddenly condense out as heavy snow, turning what used to be a routine winter storm into a record-breaking event. In the Northeast, heavy precipitation days, including snow, have climbed by 37% since 1950. Canada's Great Lakes region is seeing up to 20% more extreme snow days as well. But there is another force at play high above the surface. The Arctic is warming 3 to 4 times faster than the rest of the planet, a process called Arctic amplification. This rapid change shrinks the temperature difference between the pole and the mid-latitudes, which slows and destabilizes the jet stream. Instead of flowing steadily from west to east, the jet now meanders, looping far to the south and then back north. These deep waves let cold Arctic air plunge into the heart of North America, even as the background climate grows warmer. Dr. James Overland, a researcher at the National Oceanic and Atmospheric Administration, puts it simply: a warmer Arctic changes the jet stream, letting cold air dive deeper into North America. When this cold air collides with a moisture-rich atmosphere, the result is often snow totals that shatter old records. This collision of physics and shifting circulation patterns has become the new engine behind many of North America's most intense snowstorms. Storms that once seemed ordinary are now drawing on vast new sources of moisture, thanks to the way the atmosphere connects oceans to the land. Atmospheric rivers, long, narrow corridors of concentrated water vapor, can stretch for thousands of miles over the Pacific, carrying as much water as the Mississippi River, but in the sky. When these rivers of moisture hit the west coast and collide with cold air, they unload colossal amounts of snow in places like the Sierra Nevada. Research shows that as these atmospheric rivers warm, their moisture content can jump by up to 14% for every 2 degrees Celsius of warming. That means a single event can drop far more snow than the same storm would have just a few decades ago. On the East Coast, nor'easters tap into the warmth of the Gulf Stream and the Atlantic, spinning up into powerful low-pressure systems. These storms can rapidly intensify, sometimes called bomb cyclones, drawing in huge amounts of ocean-fed vapor. When they meet a cold air mass, the result is often blizzard conditions that can paralyze cities from Washington, D.C. to Boston. The combination of warmer oceans and a meandering jet stream sets the stage for these supercharged storms to keep happening. Forecasting these events is no simple task. As one operational forecaster explains, when you have a warm, moisture-loaded atmosphere and the right cold air in place, the snowfall potential can go off the charts. Predicting exactly where and when that collision happens is still one of our biggest challenges. The same pathways that feed nor'easters and atmospheric rivers also play a role in the Midwest, where cold air blowing across the Great Lakes can rapidly pick up moisture and unleash intense lake-effect snow. Lake-effect snow turns the Great Lakes region into a hotspot for winter extremes. Each year, as the lakes stay ice-free longer into December, cold winds sweep down from Canada and skim over the open water. That water, still holding on to summer warmth, pumps extra moisture into the air. When this moisture-laden air hits the colder land, it dumps snow in narrow, intense bands that can bury entire neighborhoods in hours. In 2022, Buffalo, New York, faced one of the most dramatic examples in recent memory. Lake Erie, which used to freeze over by midwinter, stayed open for more than 25 extra days compared to the 1970s. That December, a powerful Arctic front collided with the warm lake surface. The result was relentless. 51 inches of snow fell in just over 24 hours. Drifts swallowed cars, blocked roads, and trapped people in their homes. The city declared a state of emergency by mid-morning on December 22nd. By the next evening, highways were closed and first responders struggled to reach those in need. The impact was devastating. 39 people lost their lives, some stranded in vehicles, others succumbing to cold in powerless homes. Emergency crews worked around the clock, but the sheer volume of snow and the speed of the storm overwhelmed even the best-laid plans. As Buffalo's emergency manager explained later, power and roads fail first, and the most vulnerable pay the highest price. The story of Buffalo's blizzard is a stark reminder of how a changing climate, geography, and human systems can collide to create disasters on a local scale. Not every extreme snowstorm can be traced to a single cause. Instead, each event is shaped by a mix of long-term warming and short-term natural patterns. The El Niño Southern Oscillation, called ENSO, is one of the most powerful drivers of year-to-year variability. During La Niña winters, cold Pacific waters shift atmospheric circulation, often steering more storms into the northern US and Canada, and boosting the odds of heavy snow in the plains and Great Lakes. In the 2025 to 2026 season, La Niña increased the probability of major snow events across these regions by as much as 20 to 50%. Over the Atlantic, the North Atlantic Oscillation, called NAO, acts like a giant switch. When the NAO turns negative, high-pressure systems lock into place and encourage deep troughs of cold air to settle over eastern North America. This pattern can persist for weeks, setting the stage for repeated snowstorms. In some years, a locked-in NAO can amplify the impact of a single storm, turning what might have been a moderate snowfall into a paralyzing blizzard. Dr. Friederike Otto, a leading attribution scientist, explains that we cannot say climate change caused any one storm, but we can measure how much more likely or intense these extremes have become. Studies now show that human-driven warming has increased the probability and severity of the most extreme winter storms by 20 to 50%, especially when natural patterns like La Niña or a negative NAO align. In this new climate, the dice are loaded. Not every roll brings disaster, but the odds of an outlier keep rising. Attribution science is still catching up to the complexity of these events. Researchers use powerful models to compare today's storms to those in a world without human influence. The results are clear. While variability still rules the day, the background trend is pushing the envelope, making the most intense snowstorms more likely than ever before. When a snowstorm hits, the consequences reach far beyond the weather report. Each year in the United States, more than 300 people die in traffic accidents linked to winter storms. Roads vanish under whiteouts, and emergency vehicles struggle to get through. In rural and northern communities, the risks multiply. During a 2019 blizzard in northern Ontario, medical evacuation flights to remote First Nations were grounded for up to 48 hours. For families cut off from hospitals, a snowstorm isn't just an inconvenience, it can be a life or death barrier. Heavy snow can also cripple the power grid. In some storms, more than 1 million people lose electricity, sometimes for days. Without heat, homes become dangerous, especially for the elderly or those with medical needs. In low-income neighborhoods, outages can last a week or more, as utility crews are stretched thin and must prioritize main lines. Meanwhile, warming centers, public buildings with backup generators, become a lifeline. Cities that invested in these centers after recent storms have seen fewer cold-related deaths, showing that adaptation saves lives. The future holds even greater challenges. Climate models project that the most intense snowstorms in cold regions could become 10 to 30% more severe by 2050. Municipal leaders are responding with practical steps, burying power lines to prevent outages, upgrading snow removal fleets, and using AI-powered forecasts to target resources. Some towns have started pre-treating roads before storms hit, reducing ice and saving lives. These changes do not eliminate risk, but they give communities a fighting chance. As the odds of extreme storms keep rising, preparedness and adaptation are becoming as important as the weather itself. Each winter now brings higher odds of record-breaking storms, driven by a warming world and shifting climate patterns. For millions, that means greater risks and harder choices. As the atmosphere changes, so does our reality. Adaptation is not a distant concern. It is the new normal. Share your thoughts below.